So, we are discussing real crystal structure. So, there are special structures. One we have discussed is the sodium chloride structure. Where basically is in FCC lattice, the basis sodium chloride bases are attached. So, we have seen that sodium chloride these two are attached with each lattice point, and they are basically distant sodium and this chlorine. The distance is half of the body diagonal. Okay. So, that here I explained. So, here I have explained that this is the, if I just consider the brown one, and this is the position of sodium or chlorine, right. So, sodium or chlorine. So, you can see this, then it is FCC, right. So, each 8 corner, 8 are there, and then in each face, right, each face 6 faces. So, 6 are there, right. So, so chlorine, if we consider this the chlorine brown one, then white one is other one, this sodium one. Okay. So, sodium is placed in such a way that, as I told, that their basis sodium chloride basis, that distance between the basis and distance between the sodium and chlorine in that basis is half of the body diagonal. So, for this sodium, so this will be the chlorine. So, this sodium and this chlorine, this is one basis. Okay. This sodium will have the chlorine this one, right, will have the chlorine this one. So, this is another basis. Similarly, these two will have the basis, right. So, this way you will get 4 bases overall. If you see, because there are many atoms, but we have counted that how many lattice point or per unit cell. So, that is 4 lattice point per unit cell. So, that we have we can get the coordinate of each 4 bases, right. So, that is very important, that we will see later on. So, this how bases are distributed, if you consider the origin and then with respect to that what are the coordinates. So, that one can easily tell. So, this model is very helpful, and drawing picture also one can nicely show the position of bases and their distribution in the crystal. Okay. So, now I will go for another structure. So, crystal structure, real crystal structure. So, basically this diamond structure. Okay. So, carbon in diamond form, how it has crystal structure. So, that basically a diamond like sodium structure, sodium chloride structure, sodium chloride have that structure, but the same structure followed by the other materials. There this, as I showed, this potassium chloride and then magnesium oxide, silver bromide, right, for sodium chloride structure. Similarly, diamond structure. So, here it is again, this is FCC structure, FCC lattice. Now, in FCC lattice, earlier we have shown this how sodium chloride are distributed, right, or potassium chloride are distributed, magnesium oxide are distributed. So, in same FCC Brevis lattice. Now, here this we are telling another structure, another name we have given, this diamond structure, that is the same Brevis lattice, right, but there must be distribution of basis will be different from that other one, right. So, basically this name has come, as I told, this depending on the distribution of the basis in that same structure, right. So, here we have to find out how the bases are distributed in the structure, in this structure which is called diamond structure. So, I will show you in model, then it will be easier to understand. So, basically if you see this one, right. So, FCC structure. So, for just one can FCC structure, right. So, this is the diamond structure. So, first we need basically FCC structure, right. So, just let me draw also, then it will be. So, just if I draw the so, FCC structure cubic. So, I will carbon say in each corner, right, and in each face, middle of the face, I will put middle of the face, I will put middle of this face, I will put, and I have this face, I will put carbon. So, then I have this face. So, for this I have so I will put here for this one, I will put here, and for other face, this face, right. So, I put here. Okay. So, this is the FCC structure. This is the FCC structure. So, at each lattice point I have put carbon atom, right. So, then so this is not sufficient for diamond structure, okay, or carbon structure in diamond form. So, there are some more atoms, carbons are put in this FCC. So, they are put as a basis, additional basis point. So, how they are put? So, here let me tell, and then I will show you in model. So, if you take this, so from top, if you take this diagonal, okay. So, if you this the face, so this one diagonal, okay. So, basically you have to come down to towards the diagonal, or 1/4 towards the diagonal. If you come 1/4, so it is basically this way, okay. So, this is down below, okay. Then this is FCC one. So, if I go this way, then again from here 1/4 down, okay. So, these two additional atom are placed. So, 1/4 below of this top one. So, 1/4 this along the diagonal we are going. So, other side from bottom. So, I have taken this diagonal, I have to take the phase diagonal basically. I have to take the opposite another, so not this one, so other diagonal. From here again, if I go 1/4 up along the diagonal, so this will be then this is the phase atom. So, 1/4 I will go say this way, 1/4 I will go say this way, okay. Then this the 1/4 this way going up inside, then this, okay. So, this the diamond structure, you know. So what we are seeing this FCC structure. So, 4 lattice point per unit cell, right, 4 lattice point per unit cell. So, 4 carbon atom is there, right. Additional 4 carbon atom I have put, one is this, another this, and 2 more here. What are the position? Just 1/4 off. So, if it is 1/4, so this actually, as I told this, you have to along the diagonal, body diagonal, you have to go 1/4, okay. So, along the axis 1/4, then 1/4 and then 1/4, okay. And this other one I have to go here. So, this half then is 3/4, 1/4, 1/4, okay. So, that will be the coordinate of this from this corner. If I, so, for this one what will happen? 1/4, 3/4, 3/4, right, because this is coming from other diagonal side, okay. And this one will be 3/4, 3/4, then 1/4, then 3/4, okay. So, this will be the coordinate of this one. So, whatever I describe here, so I will show you in model. I will show you in model. So, this is the diamond structure, you know. So, first confirm that FCC structure. So, 8 corner, right, 8 corner, 1, 2, 3, 4, 5, 6, 7, 8 corners. So, 8 atoms are there. So, here just 1/8 is shown, because 1/8 you know this each corner point have 1/8 contribution in this cube, right. So, and this you see this 6 faces, and each face is having 1 atom. So, it is shown half because it is contributing half to this unit cell. So, 1, 2, right, 3, 4, 5, 6, right. So, 6 surface, 6 atoms are there. So, these are FCC. Now, additional, I told additional atom. So, if I take this way, right, if I take this way, so if this is the corner, if I take from this corner, so along the phase diagonal, along the phase diagonal, right, along the phase diagonal. So, I have 2 additions, as I told this, it's this the one, okay. What will be the coordinate? So, is the 1/4 and then 1/4 other side, and then going up 1/4, right. So, this one, right. So, this one basically, and then as I have done this way, and then this means this phase 1, and then that means half, and then again 1/4 up, So, this one. So, this atom, right. So, what will be the coordinate of this one? So, this basically if this is 1/4, 1/4, 1/4. So, this coordinate of this one will be 3/4, 3/4 and then up 1/4, right. So, these two atoms coordinate one can fixed, and then this diagonal I have considered phase diagonal. So, on top it will be just as I told, this other one I have to consider. So, this one. So, this diagonal if I consider the same way, just go down 1/4, then in middle up on the face, already it is there, then from there again you go 1/4 along the body diagonal. Okay. So, 1/4. So, then this corner. Okay. So, what will be the coordinate of these two, of these two additional? So, if I consider this one, so this is basically I will along the x axis I will go 1/4, then along the y axis I will go 3/4, right. Along the y axis I will go 3/4, and then I have to go up 3/4, then I can reach here, So, this coordinate will be 1/4, 3/4, 3/4, right. And other one, so this one, so along the x axis I will go 3/4, and then along the b axis I have to go 1/4, and then along the c axis I have to go 3/4. Okay. So, so this is another position of the additional atoms, that's basically additional basis. So, so from here also you can, I can see, you can look. So, this yellow, this is basically it is telling the position of the lattice point, right. So, in each lattice point that is carbon are there, and additional 4 carbons, this blue one, blue 4 balls you can see it is there. So, again this you see from bottom surface, bottom face. So, along this diagonal, okay. So, 1/4 of both are in 1/4 of, and axis wise you can find out this A will be 1/4, B will be 1/4, and height is 1/4 for both, height is 1/4, C will be 1/4, right. And for this one, so this is x, A and B will be 3/4, 3/4, and height is 1/4, right. And this top one again, this just opposite diagonal, phase diagonal, right. So, here this just 1/4 below or 3/4 of. So, what will be the position? 1/4, 3/4 B, and then your C along the C axis 3/4, and this one. So, 3/4 along the A axis, 1/4 along the B axis, right, 1/4 along the B axis, and 3/4 along the C axis. So, you can locate the coordinate of these 4 additional bases. So, in FCC structures, now if bases are placed in these 4 additional bases are placed in this 4 position, okay, structure will be called diamond structure, right. So, so this here this whatever as I told, this coordinate will be 1/4, 1/4, right, in terms of A, B, C, but since it is cubic crystal, so it is all A, 1/4 of A, 1/4 of A. So, this the along the A axis, along the B axis, and along the C axis, 1/4, 1/4, 1/4 this position, and this position will be I think at this it will be, this position will be I think 3/4, right, along the axis 3/4, along the B axis you have to go 3/4, and then height is 1/4, right, height is 1/4, right. So, similarly this one, additional one, this additional one, we will have this 1/4 along the axis, then I have to go 3/4 because it started from this corner. So, this 3/4, okay, and this height is 3/4. So, for both this height is 3/4, for both height is 3/4, and position of this one, coordinate of this one will be I will go 3/4, I have to go 3/4, then I have to go 1/4 along the b axis, 1/4, right, 1/4, and then it is height is 3/4. Okay. So, one can locate fixed the position of the additional 4 bases in FCC lattice. Okay. So, then this is diamond structure. So, it is the common name now, because not only diamond follows this one, this structure, other materials follows like silicon, germanium, right. So, these are the materials, other many materials. It follows the silicon carbide, gallium arsenide. So, these are material follows the diamond structure. Okay. So, since other materials following, there are many materials follows this structure, distribution of the bases is like this. So, that is why this is a common structure. For other materials we refer this structure. Okay. So, that is the basically diamond structure. Okay. So, this material have this structure is we use very frequently, because these are semiconductor material, and this whole electronic industry based on semiconductor, computer, mobile, whatever the electronics instruments they are using, all things are made from this material. Okay. So, I will discuss more when we will study the semiconducting properties of material. So, we will discuss more about this. So, there are few more structures, very interesting structures. Let me discuss. So, next one I would like to this third one, I can say this hexagonal closed packed structure, hexagonal closed packed structure. Okay. So, this also is common name, many materials follows this structure. So, hexagonal. So, hexagonal, this 6 okay, 6 faces are there, 1, 2, 3, 4, 5, 6. Okay. So, in hexagonal closed packed structure, I think I will not draw, it will be easy to show you from this picture, okay, model. So, this is the hexagonal closed packed structure, Okay. So, this is on these 2 layers are there basically to. So, this is the hexagonal. Okay. Hexagonal is having hexagonal structure is having this hexagon, right? Hexagon, right? So, if you just that will be the hexagon structure, right? So, additional. I think this also it is there, this also is there, and additional in between this is 3 more, these 3 more are there. yellow color. Okay. Then we will tell it as is closed packed, hexagonal closed packed. Okay. If these things are not there, so still it is hexagonal, right. But when these additional atoms are there, okay, so then it is its hexagonal structure, right. So, so hexagon, and this if addition 3 atoms is inside is there, so then it is hexagonal close packed structure, right. So, so this is one hexagon close packed. So, that's another set. So, this one way one can continue, right. So, here interesting thing is that each how many then in hexagonal structure, how many lattice point per unit cell, per unit cell. So, these are basically one unit cell, right, one unit cell. Okay. So, all are lattice point. Here I have not put any basis, this is lattice point. So, this so here this 120 degree, this angle is 120 degree, you know. So, I can accommodate, so 3 more hexagon attached with this. So, each corner will have 6 hexagon, will have 6 hexagon, right. Each corner this will have attached with 6 hexagon. So, how many hexagons are there? How many points are there on each face? 1, 2, 3, 4, 5, 6 at each corner. Okay. So, each one is sharing with 6. So, from this 6 I will get 1 lattice point, from this 6 I will get 1 lattice point. So, 2, and then you see this one is sharing with 2 hexagon, right. This one is shared by 2 hexagon, this is 1 hexagon, this is 1 hexagon. So, for each cell its contribution is half. So, from here and here, this from top and bottom surface. So, these 2 are there. So, I will get 1. Okay. So, 1 plus this each how many I am getting. So, from each 1/6, okay. So, from this 6 I will get 1, right. From this 6 I will get 1, so 2, and from this 2 I will get 1, so 3, and then you have 3 more inside. It is not sharing with any other unit cell. So, these 3, no. So, these 3, so 3 plus 3. So, number of unit cell per unit hexagonal close packed structure is 6. Okay. So, so it's really close packed. Why? Reason is that this you have seen this in case of FCC, it is 4 lattice point per unit cell. In case of BCC, you have seen 2, for simple cube it is 1. Now, for this closed packed it is 6, although that way I cannot say, but it has more lattice point per unit cell, but this volume also higher. So, so if one calculate, then one can show this for hexagonal closed packed structure. This packing fraction is again for this case it is 74%. Okay. So, this is same as the FCC. So, FCC structure also very close packed, and this hexagonal structure also very close packed. Okay. So, this hexagonal structure, this is the very common structure for many materials. So, this way the atoms are arranged. Okay. So, I am not drawing this one, I think I could explain from this figure, right. So, I think just I will mention 2 more structure, common structure. This is I think third one I can, fourth one is basically is also very common structure for many materials. Zinc sulfide, or it is called zinc blende structure, zinc blende structure. Okay. So, this structure, this is the same structure as this diamond is having, means it is FCC structure. Okay. So, in FCC structure whatever we have seen, in FCC structure whatever we have seen this in case of diamond. So, FCC yellow position of the yellow ball or this FCC, position of the ball is FCC, right. So, all 8 corner and this all 6 faces are having the right. So, now if in case of diamond structure, so inside this 4 additional atom was this of same material, this same carbon or silicon or germanium. Okay. So, in case of zinc blende, so if corner this FCC, this lattice point, if you put there this zinc and then this sulphide will be these just blue balls. Okay. Additional these 4 atoms. So, it will be that blue balls. Okay. So, so if it is not same material, it is different material. So, then we tell it is a zinc blende structure. Okay. So, it is basically same structure as diamond is having. So, it is just a different name. So, there are different materials which follows this structure. I can tell this zinc sulphide, that is there, zinc sulphide, and then copper chloride, indium antimonide, copper chloride, indium antimonide. So, cadmium sulphide. Okay. So, these are having this zinc sulphide structure or zinc blende structure. Okay. So, they are having these 2 different atoms. Okay. So, this so this just because of that this it is given different name from this diamond structure, but basically it is diamond structure. Okay. So, I think these are the most important, and another is there this cesium chloride structure. This some material follows this structure, cesium chloride structure. Okay. It is basically simple cubic structure. So, all each 8 corner will have the cesium, and in middle it will be the chlorine one. I think this I can tell cesium chloride structure. So, this is the cesium chloride structure I can tell. Okay. So, here you can see this 8 corner are having 8 atoms, and in middle different atoms. So, if they are cesium, then middle one is chlorine. Okay. So, its lattice point for unit cell is 1 simple cubic, that is why it is simple cubic, but additional that is basis. So, this cesium 8 corner 1 and this to form the cesium chloride. So, basis is cesium chloride. So, that chlorine is thus at the middle. So, it is not body centered, it is simple cubic, and basis is just 1 cesium chloride. So, then this structure is called cesium chloride structure, and there are many material follows this structure. So, I think we will discuss later on when we will discuss properties of different materials. Okay. So, these are the very common name of real crystal structure, where the distribution of bases are different, although this Brevis lattice is same. Okay. So, I will stop here. We will continue in next class some this crystal, as I told, this crystal bindings or crystal bonds, different kinds. So, that we will discuss in next class. Thank you very much.